Our next two examples build our confidence in solving linear inequalities. Best part about this section is we're really not adding much new. If we're able to get an inequality and graph it, like we just did in the last example, if we're able to then generate interval notation, all we're doing is now solving the same way that we've learned before and using the same principles. There's one hiccup that's going to come up in example 5, but for right now, everything's operating just under the same pretenses as trying to solve for x. The big thing that we want to focus on is at the end of the day, I want to have x on the left so I have appropriate interpretation, and I'm either going to have a less than or I'm going to have a greater than symbol, and it's somewhat dictated by what happens up above. So right here, there's nothing different. This is straight up linear solving. I have x that I'm trying to isolate. If I have x plus 3, I want to subtract 3 from both sides. These are the easy ones. Don't make them hard. So this is going to end up becoming x is less than 5. I have accomplished my goal of isolating the x variable on the left-hand side. I have an inequality symbol that says it's less than 5. All I did was subtract 3 from both sides. Now, I have established that x is less than 5 by using the addition property. I have that established. So what we're going to then focus on is saying, okay, how am I going to graph this? So I need to graph this solution set that says x is less than 5. Somewhere down on this graph, there's going to be a value of 5, there's going to be a value of 6, a value of 4, and there's going to be other additional marks, 4, 3, 2, 1. And we can establish that x is less than 5 going off our graphing. I want to know that I need to make a mark, and it's either going to be a bracket or a parenthesis, and I need to know which one. The first thing that I do know is a less than is going to tell me that from 5 I am coloring that way. So all of these numbers work, and we're establishing the less than part, and we're going to use the parenthesis because I have the less than. So here is my graph, a little bit choppy, but a graph nonetheless. Now, moving to interval notation, I always do the graph first, because when I go to interpret interval notation, I want to look at my graph and I want to say, okay, coming from the left, who's the first number colored? It's negative infinity. Carrying on from negative infinity, where do I stop coloring? And I stop coloring at the number 5 with a parenthesis, meaning that I don't get to include 5, which this parenthesis then shows that, and it shows that, so I get the appropriate interpretation. Now, if I want to write this in solution set form, so I'm identifying these little curly braces that might be a little hard for me to write. I've got a curly brace, and we're saying that the solution is a set of x's such that x meets the condition of being less than 5. So here is my solution set. What are we doing here? We're solving. We are solving a linear equality. We are finding the values of x that make the original statement true. Well, every time you pick a number that is less than 5, this will be true. If you plug in the number 6, 6 plus 3 is, less than. It has to be less than 5. You plug in 6, 6 plus 3, 9 is not less than 8. It is not part of the solution set. If I plug in the number 4, 4 plus 3 is 7. Is 7 less than 8? Yes. How about 0? Well, 0 is less than 5. It should work also. 0 plus 3 is 3. Is 3 less than 8? Yes. The difference between inequalities and equalities is the fact that we get a solution set, a large group of them that will work. Our next example, we have to move a little bit more, a few more terms to be able to get my x isolated. Again, remember, my goal is x on the left and a constant on the right. So I have an x variable over here, so I want to subtract 3x so that I'm going to isolate my variable. I also want to add 1 to both sides because I want to get the constant term on the other side. This is going to give me x. My symbol is a greater than or equal to. Those go away, and I'm left with negative 5. So x is greater than or equal to negative 5. I have accomplished my goal. Let's go ahead and do the solution set right now. It is that simple. Do not make this step going from here to here difficult. You've already solved it. You've said pick an x, any x, as long as it's greater than or equal to a negative 5. It's the set of all x's such that this condition is met. And that condition is x must be greater than or equal to negative 5. Interval notation, let's not do that yet. Let's go down to our graph and let's go ahead and graph it. Somewhere in the world there lives a negative 5, and then there's going to be a negative 4 to its right and a negative 6 to its left. And if I established that x is greater than or equal to a negative 5, I'm going to use the symbolism that I use my bracket, because the bracket establishes it's going to be a bracket. The arrow establishes that I'm going that way. I've got it all together, and here is my graph. Now from my graph I can easily say, coming from the left, who's the first one who's green? It's a negative 5. I carry on coloring until when? I don't ever stop, so I go on to infinity. Infinities always have parentheses on them because you can never include infinity. It's always a bigger number. I've used the bracket on the left because of the equals to part of the greater than or equals to, and it's also the piece that's on the graph. So those are all three parts of that answer.